Okay, so this is lesson 4.2, Scatterplots and Lines of Best Fit. So yesterday we talked about how to plot ordered pairs or plot points. Today we're going to talk about plotting more than one point and sort of coming up with some information about them, making some predictions and organizing that. So today our goals are to draw a scatter plot. Can we put all these points into a graph and choose proper scales and all of that stuff? Can we draw a line of best fit? And there's an interesting point that I'll come back to in brackets after that. We're going to interpret that information, so, sort of talk about what that means, and we're also going to make predictions about the information that we see, okay? So the first example that I'd like to talk about is graphing this set of data. Now, yesterday we talked about X's and Y's, so what's really neat about this information here is obviously, this is basically an ordered pair, 5, 9, right? We would be able to graph that. The first thing, though, before I say sort of grab some graph paper and go is, I want you to intuitively know what type of a graph we're going to go for. But what does that mean? Well, we have a few different graphs in our sort of ability to graph, right? We have this one graph that's sort of like a cross, and we have this one graph that's kind of like an L-shaped graph. And the real question I would want to ask you is, like, which graph do we choose for this set of data? Well, I would suggest that this cross graph actually is probably not what we want to go for. And the reason being is there's no negative numbers here, right? The cross graph, as we saw yesterday, deals with negative numbers, right? And our negative numbers here and negative numbers here. Well, look at our table of values. There's no negative number there, okay? So if there's no negative number, we don't need negative numbers. We don't need a cross graph. We actually would be more efficiently to use the L-shaped graph here, right? That's nice and it covers a lot more information. It's a little bit more efficient, so it's a better use of our space and time, okay? So if we wanted to graph this pairs of information, I'm going to pause my video and graph it so that there's no dead air, but you could probably be able to see where all these points would go, hopefully. Okay, so just a little bit of background on how I graphed these, so I know this magically seemed to have appeared. A few things before I start. You can choose a scale that's appropriate, right? We don't want to sort of just go up to 60 halfway through our graph. We want to go up to 60 close to the top of it. I chose for each square to represent 5 units. I chose here for the x-axis to represent, 1 square to represent 2 units. You can choose whatever scale you want. Just make use of the space that you have. You don't want to wind up not using enough space, and you don't want to wind up running out of space. That's why you do graphing with a pencil, right? So if you accidentally choose the wrong scale, or you mess up while you're doing the scale, you can erase things, right? Don't do graphing in pen. So I've plotted all of my points, and again, these are more or less the points. It's not an exact sort of a science here, just plotting these points, okay? And they look pretty accurate. Most of you know this from your science classes in the past, or at least hopefully you know based on common sense, like what I might mean by a line of best fit. But what's a line of best fit? It's a line that best fits the information. So you take out a ruler and you draw a line. Now, you don't draw just any line. You draw a line that more or less fits this set of data. Now, some people will say you have to have the same number of points above as the same number of points below. I don't like that analogy. What you want is a line that's as close as possible to all of the points. Right? Because if I said, a line that has the same number of points above as it does below, you would draw a line that looks like this, right? Oh, well, there are 3 points above and there are 3 points below, aren't there? That's not really the line of best fit, though, right? It doesn't really fit the data, right? This point over here is kind of far away, and so is that point. We want one line that models all of this information as best as we can. So we draw a line that touches, or at least comes close to touching, as many points as possible. It fits the best, okay? It doesn't fit perfectly. Some of the points aren't exactly on the line, but that's okay. So that's what I mean by a line of best fit, okay? So the second example, now dealing with negative numbers. So immediately your mind should go to what type of a graph am I going to pick? I'm not going to choose the L-shaped one. I'm going to choose the cross one that we talked about yesterday with ordered pairs because there are negative temperatures going here. Okay, so for our American friends that are checking out this video, I apologize, right? We're in Canada, we're using metric, so I'm using centigrade, I'm using Celsius, okay? So we're talking about temperature, goes into the negatives after we're measuring it using time and minutes. So another interesting thing to discuss is sort of how you choose your axes. Well, usually when data is presented to you, it's presented in order. So usually X is on the left and usually Y is on the left, on the right. But you see your time, it goes up by a pretty regular pace, and that makes sense because the scientist that's taking these temperatures is checking the temperature every minute, right? you're choosing to check that temperature. It's an independent variable, right? So X is your independent variable because that goes up by the same amount each time. Now your independent variable is always on the horizontal, it's always X. So in this case it's not X, it's time, right? So you can label it time. And of course your temperature is your Y, so let's label that. Okay. And again, you choose an appropriate scale. So I'm going to pause the video and show you my scale. And we're back. So now you can see all of these points plotted as well as my temperature and time. You can see that I don't have my scale written here. That's probably bad form on my part, but I use each square to represent 5 degrees Celsius on the vertical, and I use each square on the horizontal to represent 1 minute of time. Okay, so you know, we have a scale. I haven't really indicated it. Maybe I should be a little bit better about that to do so. Okay, so I'm going to show my scale. This is 20, this is 10, this is negative 10, this is negative 20, and this is, you know, 1, 2, 3, 4, etc. Okay, so you can show a few numbers to show a scale. But like I said, the main piece of this lesson is, can you draw a line of best fit? Let's go for it. There's a line that pretty much, you know, it comes close to touching all of them. It's not an exact science, but, you know, you can play around with the line and move it, get it to the right spot. So before you use your ruler to draw the line, you know, check. Is it close to all those points? That's close enough for me. Okay, great. So that's a line that models this information that's going on. Now I know, you know, we don't really have such a thing as negative time. I mean, we could talk about 1 minute ago. So I guess fair enough. The line could extend into the negatives for time. Our data doesn't, though. Okay, so it'd be dangerous to assume that. Anyway, so we got this situation. Here's the information. What's neat about this is that we could make predictions based on this information. I could ask, you know, what will happen at minute number 7? But what if I actually, you know, just counted up over here, like 1, 2, 3, 4, 5, 6, 7. And I said, well, if this is 7, I could count down and take a look at where this green line is at 7 minutes and sort of look at what the temperature is based on my line of best fit, because my line of best fit models that information. My line of best fit is suggesting that around 7 minutes I have something that's, you know, close to negative, you know, close to around negative 31 degrees, you know, like give or take. That's an estimation. Eventually we'll come up with an equation for this, but for now, you know, negative 31 degrees would be a good estimation for 7 minutes into this situation. Okay, so there you are. That basically is how you would make a prediction as well. So now we covered basically everything about the lesson. Let's put it all together in one last example. Okay, the table that shows the height and mass of 12 soccer players. Now, those numbers are super tiny. You can go to our course website and take a look at those actual numbers, or you know, you could just sort of take my word for it. I'm about to plot all of those points. Okay, so I'm going to pause my video again, plot all of those points for you, and we'll talk about that. Okay. And we're back. So you can see I've plotted a bit of information. Now I've been a bit naughty. I've used height actually as my y-axis. Now what's interesting about this situation is there's no independent or dependent variable, okay? I'm choosing to use, you know, the height is my y-axis or the mass is my x-axis. You could have chosen differently, and I kind of hope you would have, because I said in the previous slide that the first column, the leftmost column, is actually x. Okay, but you know, for now, it's getting late in the evening, as you can see. So I'm going to finish off with this. I've plotted all of my data based on that information, and actually it doesn't really matter which one you choose as y or x, okay? So in any case, I'm going to draw my line of best fit, okay? I'm going to do it black this time so we can see everything else I'm about to do, but that's, you know, that's more or less. Remember, of course, you know, you can play around, you can toggle that line, you can move it up or down a little bit, okay? But, you know, that's the best thing. Now, a few interesting points, hopefully you understand this. These little symbols that I drew in here suggest that I'm not starting at 0, okay? It would make no sense to start my graph at 0 because nobody has a height of 0 centimeters and nobody has a mass of 0 kilograms, right? So, for example, there's no point in starting off with those numbers. We use those little symbols to say there's a break, okay? There's a break in the data. It starts actually at 150 for the height and at 50 for the mass, okay? And then after that, I had my own scale, as you can see in the numbers that I typed in. Okay, so all of my purple little dots represent each different player on this team. So there's all of that information in line of best fit. So graph the data, draw a line of best fit, check mark, we're done, great. Predicting the mass of another soccer player in that league whose height is 170. All you got to do is look at the graph. Oh, okay, well there's a height of 170 right here. If you look straight across as a line, you can see that your line of best fit, it actually hits the line of best fit at a particular point. And if you follow that line down, you can actually almost like magic see a mass, right, for that particular point. Predicting the mass is as simple as just looking straight over and straight down. Okay, so the height, 170, look over towards the line of best fit. Once you hit the line of best fit, go straight down to the mass, 62 kilograms is a good prediction. You know, and again, this is an approximate prediction because your line might be a little bit higher or lower, steeper or less steep, okay? So whatever, we're close, around 62 kilograms. Predicting the height of another soccer player in that league whose mass is 50 kilograms, we kind of do the opposite. So I'll just change color. 50 kilograms, well, we would look straight up from 50 kilograms, which is right here. We'd go straight up, oh, and straight over. There we go. Okay, so I think based on my graph, yeah, that's about 158. So, you know, roughly 158 centimeters, okay? And again, these are estimations. They're rough, okay? But they're good predictions, right? So they give us a little bit of background information into a situation, what to expect, what to assume, and see. So, you know, going way back to the very beginning of my lesson for today, you know, have we done what we needed to do? Hopefully by now you know how to draw a scatter plot. Choose the correct axes, label them, okay? Choose a scale that fits everything and uses everything efficiently. We can draw the line of best fit. Now this point in brackets now kind of makes sense, okay? Let's look at some of our examples. This one here looks like it goes through the origin, right? It looks like it goes through 0, 0. That's fine, but that might just be a happy coincidence. Because take a look at a few of the other examples. Our temperature versus time graph. You can see that this line does not go through the origin. Okay, right? That's fine. The line just doesn't go through 0, 0. A very, very common mistake when people are drawing lines of best fit is that they just sort of force it to go through the origin. There's another example here of a line that just doesn't go through the origin, okay? So please make sure that when you're drawing a line of best fit, you're not forcing it to go through the origin, okay? Now I'm going to pause the video, we're going to talk about a few quick little terminology things, but that's pretty much the crux of the lesson, so you're okay to move on. So a few last minute points, pun intended. We've got a whole load of points here on a graph, right? So if I was going to ask you to draw a line of best fit, I hope you'd probably say, Mr. Pereira, I can't. Because there is no line of best fit to fit all of that information. In fact, in mathematics, we say that there's no correlation here, no correlation. So all of these past examples that we looked at have a correlation, right? There are points close to a line. There's no way I could draw a line that would model this information, so there's no correlation, okay? So say, for example, that I drew some points that actually did show a correlation. I'll just erase these nice and conveniently and draw a few more. So say, for example, that I had these points sort of going in this kind of direction. Well, you can see actually that that would have a line of best fit, right? There is a correlation. All of those points have a line, you know, could be modeled like that, okay? It's a bit of a weaker correlation than the ones that we saw, so it is not a strong correlation. It's not as strong as, say, for example, the mass question that we looked at. That line's pretty close to most of those points, and it's nowhere near as close to that temperature example that we looked at. That's a strong, strong correlation. Over here, it's a little bit of a weaker one, okay? We can also talk about positive and negative correlations. This line is pointing down from left to right. That's why we call it a negative correlation. It means as x gets bigger, y gets smaller. That's just like our temperature example here. Negative correlation because the green line points down from left to right. Here's a good example of a positive correlation. The line points up from left to right. As x becomes a bigger number, so does y. That's why we call it a positive correlation. In our real life example, talking about the soccer players, that's a positive correlation as well. That kind of seems logical though, right? The taller you are, the heavier you should be. The heavier you are, the taller you should be. Okay, so that's a positive correlation. It's a little bit weaker than some of the ones that we looked at because people are people, right? Not everybody is going to fit into that cookie cutter image of perfect height to mass ratio, okay? Some people are taller and skinnier, some people are shorter and stockier, okay? So that's just the way that life goes, and that's the way the data is. Okay, so I hope this was kind of useful. Again, check out the homework. It is in the textbook tonight. We did it in class, but if you're away, you're expected to do it anyway. Have a good night. Good night.